In 2011, the U.S. consumption of fuels for electricity generation in quads was as follows: coal, 18.04 quad; natural gas, 8.05 quad; petroleum, 0.29 quad; nuclear electric power, 8.26 quad; renewables, 5.14 quad. Calculate the total energy consumed during the year in gigawatt hours. And if gross generation of electricity in 2011 was 14.82 quad, what was the average heat rate for the entire system? So we're given these different amounts of energy consumption, so that's the input energy into the electric generation system of the United States. And so we'll just summarize those. Those are all energies, right? That's what quads are. It's a very common unit when energy quantities are very large. So the energy input into the coal plants total was 18.04 quad, QUAD. Remember, quad stands for quadrillion BTU, or 10 to the 15th BTU. So then we've got the energy that went into all the natural gas system plants in total. That was 8.05 quad in 2011. Petroleum. We'll use the symbol P to keep track of petroleum, just to keep ourselves organized. That was 0.29 quad. Then we've got nuclear power, energy in nuclear. That was 8.26 quad. Going to start over here now. We had some renewable energy. Give that the subscript R, E sub R. That was 5.14 quad. We also know that the gross generation of electricity was 14.82. Gross is just how much output we had in electric energy. So sum it all up. So the output electric energy, 14.82 quad. So we got our givens, so the next step is to write the finds. What is it that we're being asked to calculate? So we want to know what the heat rate for the overall system was. We're going to write average because we're just averaging it across all the different sources. How efficient on average is the electric power generation fleet, or was the electric power generation fleet in the US in 2011. And then we were asked to calculate total energy consumed, E total, in gigawatt hours. Okay, so we'll solve that second one first. The E total, the total energy consumed in input fuel sources, is just going to be the sum of E across the different sectors of fuels. So I'm just going to add those up, right? That was 18.04 quad plus 8.05 plus 0.29 plus 8.26 plus 5.14, and you get 39.78 quad in 2011. That was the input fuel. You'll notice I added them up first, even though it asked us to do it in so we need that, instead of in quad, we need that to be in gigawatt hours. You'll notice that I didn't convert each individually first because it doesn't matter what order you do that in. You could have converted each of these over to gigawatt hours and then summed it up, or you can add them all and then do the conversion. It's less math if you add them all up and then do the conversion, which is the approach I took here. So E total in gigawatt hours, we just need to take 39.78 quadrillion BTU, and we need to know how many gigawatt hours are in a quad. So we're going to take 39.78. There are 1.055 times 10 to the 18 joules in a quad. So that's one conversion step. I'm going to go from quad to joules. And then I'm going to go from joules to kilowatt hours. 1 kWh, and that's 3.6 e to the 6 joules. So you can see now quads cancel and joules cancel. That's going to leave me with kilowatt hours. I'm getting closer, but I want to be in gigawatt hours here. So I'm going to say, well, I got a kilowatt hour here, 1 kilowatt hour. Down here, there's 10 to the minus 6 gigawatt hours per kilowatt hour, or you could write it as 10 to the 6 kWh per 1 gigawatt hour, right? So this is a multi-step energy conversion process where we're using joules as an intermediate energy unit. So we're going from quad to joules, from joules to kWh, from kWh to gigawatt hours, GWH. So do all that calculation, and then you get 1.1658 times 10 to the 7th gigawatt hours. So that's how much electrical energy the United States used in terms of input fuels. If you take all the fuels that went to the power plants and everything, 1.1658 times 10 to the 7th gigawatt hours in 2011. So we were then asked to calculate what the overall efficiency, the average efficiency of the power plants in the system is. Remember, efficiency can be calculated from 3,412 BTU per kilowatt hour, the heat content of a kilowatt hour divided by the heat rate. And so we can just rearrange those to solve for heat rate. It's 3412 over the efficiency. Gives us that calculation. So we know up here that the output energy was what? It's given to us someplace. I wrote it over here. 14.82 quad. So we've got 14.82 quadrillion BTU. And we know the input energy, we summed it here, that's 39.78 quad. So we can take the output divided by the input, that's equal to the efficiency of the system. Right? And so if you do that math, you're going to get 37.3%. Clearly I already multiplied by 100, but you know that because you've done some earlier problems, right? So we're at 37.3% efficiency. If I want to state that efficiency as a heat rate, which again is very common in the power system, I take 3,412, divide that by 0.373. The efficiency is a decimal, and I'm going to get 9,147.45 BTU per kWh as the average heat rate of a power plant in the United States when averaged across all systems.